Hello everyone, welcome back to the NPTEL course on materials informatics. In today's lecture we will be continuing our discussion on lattice models and sampling techniques and focus more on the sampling techniques. So just as a recap of what we discussed in the last lecture, we looked at lattice models and their application. So they can be used for modeling or predicting phase transitions and also diffusivities in different systems. We looked at a specific example of a lattice model, which is a cluster expansion, can be used to describe any configurational dependent properties and is commonly expanded on energies. And we also looked at some of the hyperparameters associated with the cluster expansion construction itself. So in today's lecture we will be looking at Monte Carlo and how sampling techniques are generally useful to combine statistical mechanics along with lattice models. Okay, so the key in statistical mechanics, right, is always how you sample your system. So if you think about microstates and macrostate, any macrostate property in statistical mechanics comes from a robust sampling of the associated microstates, right, in your given system. So the simplest example is let's say you don't know the value of pi, but you have a circle in front of you. How do you actually estimate this value of pi, right? You can do this by sort of throwing darts, right? So how do you do this, right? So let's say I take only the first quadrant here because if I can get the value of pi by 4 in this first quadrant, I can basically multiply that with 4 and get the actual value of pi, right. So I am going to use the symmetry of the circle here and just take the first quadrant, right. So on this first quadrant I am going to basically draw a square, right, of the same radius as my circle. So here I have a circle of radius 1, right. So I am going to draw a square of length 1 here, right. So you see that the circle is completely sort of inscribed within the square, right. Now I am going to randomly throw dots, dots and basically get a measurement of how many dots are within the circle compared to how many dots are outside the circle, right. So the red dots here basically represent the dots that are within the circle, and the green dots basically represent the dots that are outside the circle, right. If you just throw like 10 dots, right, for example, you may have let's say 7 that land within the circle and 3 that land outside the circle. So that does not give you very good estimate of pi, right. But if you have considerably large number of dots, right, if you keep throwing large number of dots, eventually you will get an estimate. So if you count the total number of red dots here, that will give you an estimate of the area of this quadrant here. So area of the circle is pi r square, so area of the quadrant should be pi by 4, and then if you normalize that with the total area of the square itself, right, or take the difference in the area outside the circle, you can basically get an estimate of pi. So if you identify the total number of dots within the circle, right, and if the number of dots is large enough, then the total number of dots within the circle should approach the area of the quadrant itself, which is pi by 4. And if you also include the dots that are outside the circle, then that quantity should approach the area of the square. So you should be able to basically statistically get a value for pi by 4, right. So as long as you throw enough dots, you should be able to get a value that is very, very close to the pi by 4 value or the value of pi, right. So this is how you can use sampling techniques to arrive at quantities that are not very well known, right, or you may not have the values readily with you, right. And this type of sampling is what is referred to as simple sampling technique. Simple sampling because when you throw a dart, it can randomly sort of land within the circle or outside the circle. So it can land anywhere, right. So you don't bias where your dart actually lands, you just count the number of dots that are landing within your circle and number of dots that are landing outside your circle, right. So this is an example of a simple sampling technique. So in material science it turns out that if you use simple sampling techniques, you don't quite get good properties of your system. So let's say you have this is the number of microstates that you have in your system, so that's indicated by omega here, and let's say this is we are plotting the number of microstates as a function of energy, right. So the number of microstates generally for systems tends to increase with higher energies, right, with increase in energy. So the more energy you have, the more microstates you generally have within your system. So at a given temperature, so let's say you know, your equilibrium energy or your average energy of the system is sort of given by this quantity here. You would see that your system mostly has distribution of microstates in this narrow range, right. So this is how at equilibrium your system has a distribution of microstates. So there is no point sampling microstates here because they do not contribute to your equilibrium values or your average values here, right, and there is also no point sampling microstates here, right. So in other words, you need to sample a fairly narrow range of microstates that are relevant to your system for you to get very good estimates of your average thermodynamic quantities such as average energy here, right. So this type of localized distribution is what is referred to as importance sampling. So just throwing dots is simple sampling, this is importance sampling where we identify the region of importance for our system and then sample within that region, right. So importance sampling is what is commonly used in materials because that is computationally more efficient. So I will give you another example of importance sampling, right. So let us say you want to measure the depth of the river Nile in the continent of Africa, and let us say you have a stick that has been given to you, right. Simple sampling would basically ask you to travel across all of Africa, right, and then measure the average depth at each point, right, within the continent, and then you know, identify which of those points actually fell on the river Nile, and then take the average of those points to get the average depth of the river Nile, right. So in simple sampling you are basically wasting a lot of resources sampling across the continent of Africa here, right. But in importance sampling you would first identify the river Nile, right, and then put in data points or basically take measurements across the river Nile only, right. So identify the river and then go along the river, calculate the depth at every point and then take the average, right. So in simple terms you can see that, you know, this is actually more efficient than sampling the entire continent of Africa, right. So this is an example of importance sampling, right. So importance sampling, you identify the region of interest, right, which is river Nile here, you go to that region of interest and you sample that region well enough, right. So in materials science we typically use importance sampling because again it is computationally more efficient than using simple sampling techniques. And one way to do this importance sampling technique is using what is referred to as the Metropolis algorithm within the Monte Carlo technique itself, right. So what do we do here? So let us say you have a lattice and then you have particles within your given lattice. You can already calculate the energy of that lattice, right. So the energy can be calculated either using, let us say, density functional theory or using a lattice model. So let us say you have already constructed a cluster expansion, any given configuration of atoms, you can always calculate the energy associated with that configuration, right. So once you have the calculated energy, you can now select a particle at random and then you sort of give a random displacement for that particle, right. So the displacement can actually be a physical displacement or the displacement can be an exchange, right. So you can remove that particle, you can swap it with a different particle, right, or you can put that particle into a different site, right, within the lattice, and once you do that you can calculate the new energy again, right. So let us say that displaced energy is U of r dashed n here, and then so from your state 1 to state 2 you have basically caused a displacement in your system, right. We call these displacements as moves or steps within our system. So you then accept this move with some probability, right, and this probability is something that you can mathematically define. So depending on which quantity you are tracking, so if it is energies, we typically take this minimum function here. So if this displacement is downhill in nature, so let us say you go from r to r prime here and that causes a decrease in energy of your system, then you accept this move with a probability of 1. If it causes an increase in energy of the system, then you accept the displacement with the probability of the exponent of the difference in the energies, right. And beta term is basically what comes out from your cluster from your statistical mechanics. This is nothing but KBT, Boltzmann constant 1 over KBT, which is Boltzmann constant times temperature, right. So you take the minimum of these two. So if it is downhill displacements or downhill moves, you accept them with a probability of 1. If it is uphill displacement, then you accept that with the probability of the difference in the actual energy between the two. So this is an example of what is referred to as the Metropolis algorithm, and this is a very important algorithm that does importance sampling within our given system, and it helps us calculate phase diagrams in a fairly swift fashion. So the Metropolis algorithm is known for satisfying what is referred to as detail balance. So detail balance is a very important mathematical condition that any sampling technique has to satisfy so that we get thermodynamically averaged quantities. So if you are worried about quantities that are time averaged in nature, such as thermodynamically averaged or equilibrium quantities, then our algorithm has to satisfy detail balance, right? And we'll see what is the mathematical condition associated with detail balance in the subsequent slides. So once you implement this Metropolis algorithm, you can actually get very good statistical averages of equilibrium quantities, right? And once you get good statistical averages of equilibrium quantities such as energies, specific heats, entropy and so on, you can then use that information to calculate your phase diagrams, right? Or if you are interested just in transitions, you can also calculate the temperatures or compositions at which transitions actually happen in your system. So that is one example of using sampling techniques to calculate phase diagrams, so equilibrium quantities. You can also use these sampling techniques to calculate kinetic quantities or diffusivities. If you do those, if you use Monte Carlo to sample diffusivities, then you would typically use a technique referred to as kinetic Monte Carlo. So in kinetic Monte Carlo, one specific algorithm is what is referred to as rejection free kinetic Monte Carlo. Here again you take a given system of interest, you sort of displace a particle within your system of interest. So the displacement is usually some kind of a atomic migration here or atomic hop in the case of kinetic Monte Carlo, and for that hop you can basically calculate the associated frequency or the associated energy barrier, right, for that hop, and you can either accept or reject that hop. So if you do not reject any hop, so if you always accept them with some probability associated with them, then that is referred to as rejection free kinetic Monte Carlo. So you can basically calculate those probabilities and also update an associated time variable. So if you do this, you basically get a set of displacements of your particles and the associated times along which these displacements actually occur, and if you take the ratio between the two, so displacements divided by time basically gives you your diffusivities, right. So this in short is how kinetic Monte Carlo or kinetic Monte Carlo works, right. So it adopts the same Monte Carlo method or Monte Carlo sampling technique, right. It does introduce displacements, but it accepts them with at a given frequency, and it also tracks the associated time for each of those particle displacements that you have in a given system. Okay, so what are the conditions for ensuring that the sort of Metropolis or any sort of algorithm works, right? To ensure that we are getting statistically well averaged quantities. So they have to satisfy two mathematical conditions. One is what is referred to as equal a priori probabilities. So basically, if you are if you have a system and if you are considering any particle to be chosen for displacement, any particle can have can be chosen for the displacement, right. So so any displacement is sort of equally probable in some sense, right. So that is what is referred to as equal a priori probability. So you basically do not bias which particle you are choosing for the displacement in your algorithm, right. So that is referred to as that is the result of equal a priori probabilities. The second important condition that you have to satisfy is what is referred to as detail balance. What this means is that, so I know I'm introducing a bunch of terms here. So what this means is that the net probability for a transition from state I to state j in your system. So state I is one microstate, one given configuration. State j is another microstate, another given configuration of a system. So the probability of transitioning from state I to state j should be the same as the probability of transitioning from state j to state I, right. So that is what detail balance basically means. So Pi basically refers to the probability that the system actually stays in state I, and then Wi to j refers to the probability of transitioning from or going from state I to state j, right. So Pi times Wi basically represents the net rate at which the system can go from I to j, and same thing from j to I. So that is the net rate that the system actually can transition from state j to state I. So both the rates, so the rate for the forward reaction and the rate for the backward reaction should be the same, or the forward transition and backward transition should be the same. So that is what is is guaranteed by detailed balance, and as long as any sampling technique that you use or any sampling algorithm that you use satisfies detailed balance, you are guaranteed to get thermodynamically averaged quantities. So you can show that if you use the Metropolis algorithm that it satisfies detailed balance in a very simple in a very trivial way. So let us say you have state I which is lower in energy compared to state j, right. So I to j is an uphill climb, right. So the probability that your system is in state I is let us say 1. So you are already starting with state I, so it's that probability is 1, and then the rate of transition, right. So the rate of transition according to Metropolis is going to be exponent of the energy difference, because this is an uphill transition. So so that's going to be e to the power negative let us say delta ei I to j here divided by kBt. So this is going to be the probability term here, right. So that's the left hand side. On the right hand side we have Wj2i is a downhill transition, so that will have a probability of 1, but the probability that your system is actually in state j, right, will be lower, right, because system j is at a higher energy compared to system I, microstate I. So microstate j is at a higher energy, so the probability that the system itself will be in that higher energy state will actually be dependent on your exponent of the energy difference, right, between your I and j, because I is at a lower energy compared to that of j. So Pj will actually if you do the math, it will basically be exponent of negative delta E I to j divided by kBt here, right. So basically we made the assumption that Pi has a probability of 1 and Pj has a probability of e to the power negative delta E. The way we actually calculate it is Pi will have a probability associated with the exponent of the energy associated with that microstate. Pj will have a value of exponent of negative Ej, and we basically take the difference between the two. So if you divide Pj by Pi, we basically get 1 here and e to the power negative delta E here, right. So to very simply put, if you use Metropolis sampling technique, you will very trivially satisfy detailed balance, right. So the probabilities of the individual microstates multiplied by the rates of transitions for the microstates will be equal, depending irrespective of whether you go from downhill, whether you go along an uphill direction or in a downhill direction, okay. So in the case of Metropolis, right, so how do we practically implement Metropolis? So we have to do the sampling at different temperatures as well as different supercell sizes. So we typically when we build a cluster expansion, we build it in a smaller cell, and then when we do Metropolis or Monte Carlo, we have to sample them in a larger supercell or larger condition, so that we can actually get the phase transitions more accurately. So we do it at different temperatures and larger supercells or different supercell sizes. Typically we start with a random configuration, we choose perturbation. So perturbation here is a flip of spin or flip of an atomic species, right. So if you have atom A, you either remove it or you change it to atom B, right, and then you compute the energy associated with that, and this calculation of the energy comes from cluster expansion, right. So cluster expansion is a lattice model, it is a fitted model, so the energy evaluations are very quick, right. So if you were to rely on DFT for individual energy evaluations, you will see that you will require a lot of computation resources and also a lot of time, right, which you may not have. So that is why the cluster expansion comes in handy here. So once you calculate the energy, we can then calculate the rate of transition. So if it is downhill, then we set the rate of transition to 1, and if it is uphill, we set the rate of transition to be exponent of negative delta E, right. So and then once we accept the transition, we then choose the next perturbation, right, accordingly. So once again, so Metropolis should satisfy detailed balance. So this Pi is basically e to the power negative Ei by kBt, Pj is e to the power negative Ej by kBt, and then you have W I to j as the delta Eij term here, and then this Wj2i will be 1 here. So you will see that LHS equals RHS when you do the math with respect to Metropolis algorithm, right. Okay. So one thing we should note about Monte Carlo, just like molecular dynamics, is that we need to equilibrate our system. So when we start sampling our system, at least for the first few times that we create perturbations within our system and do sampling, we won't get very good statistically averaged or thermodynamically averaged quantities, right. So this is similar to the throwing darts case to estimate pi. So if you throw too few darts, you are not going to get a very good value of pi, very good approximation of pi. So you need to use sufficiently large number of darts or sufficient number of sampling steps to ensure that you are actually getting values that are closer to the quantities of interest for you. And typically we sort of pick a quantity. So the way we converge or equilibrate Monte Carlo, just like equilibrating molecular dynamics, is we pick a quantity and then equilibrate that within a threshold noise or tolerance, right. So one common quantity is some kind of energy or a normalized version of energy here. So this is E by Kb, so this is basically a temperature quantity here. And we sort of ensure that this quantity, the energy or some kind of scaled energy converges to a certain threshold as a function of number of steps, right. So there is also one thing that you should note about in equilibrating Monte Carlo in terms of terminology. So there are some people who report number of steps that they use for equilibration. Some researchers use the terminology of sweeps, right. So this has similar connotations to iterations and epochs in machine learning models. So in the case of machine learning models, one iteration is basically any update in weights and biases that you have. So if you do forward and backward propagation, it is basically one forward propagation, calculation of loss, and then one backward propagation and updation of weights. That is one iteration. And if you sample all the data points in your training set, that is basically one epoch, right. So that is the terminology that is used in machine learning models. Similarly, in the case of Monte Carlo, step is basically any displacement or any perturbation that you introduce in a system, that is a Monte Carlo step. A Monte Carlo sweep is if you have introduced the same number of perturbations as the number of distinct lattice points in your system. So let us say you have 100 lattice sites in your given structure. If you have introduced 100 perturbations in your Monte Carlo sampling, then that corresponds to one Monte Carlo sweep, right. So if number of Monte Carlo steps equals the number of lattice sites, that is one sweep, right, and every perturbation is basically a Monte Carlo step, right. So typically when you think about Monte Carlo steps, right, so the number of steps that you would need to equilibrate can very easily be about 100,000s, easily tens of thousands, very easily hundreds of thousands. In terms of number of sweeps, this will be usually of the order of 1000 or 1500 sweeps. Okay, and then comes the important question of how do you detect phase transition. So let us say you built a cluster expansion model, you did Monte Carlo sampling, how do you actually detect phase transitions, and if that is your interest in building phase diagrams. So in phase transitions there are two major types, right. So the first order and second order phase transitions. First order transitions have a discontinuity in the underlying thermodynamic potential. So let us say you think about Gibbs energies or Helmholtz energies, they will have a discontinuity, a well defined discontinuity in their first derivatives. So the first derivatives are typically entropy or volume, for example, right, and these can also be and these discontinuities are easy to visualize. So if you plot it as a function of energy versus temperature, you will see a change in derivatives, a change in slope in your energy versus temperature curve. In your concentration versus chemical potential, you will actually see a step, right. So in first order this is actually fairly easy to detect phase transitions. Second order is the more difficult version, because in second order transitions there is a discontinuity in the second derivative of the thermodynamic potential. So for Gibbs energy or Helmholtz energy, that is the second derivative of these values with respect to either temperature or composition. So that is typically specific heat. So if you take the second derivative of Gibbs energy with respect to temperature, that is your specific heat at constant pressure. And if you do the same exercise for Helmholtz energy, that is specific heat at constant volume, right. So for detecting second order transitions, we actually need to keep track of specific heats, right. And specific heats, as you are probably already aware, are basically the sort of perturbations or oscillations in the energy during your sampling itself, right. So when you calculate, when you consider statistical mechanics, right, so it is the variance of the energy itself for your collection of microstates in a system that corresponds to the specific heat of the system, right. So when we do sampling using Monte Carlo, we can straightforwardly calculate specific heats, right, and we can then use these specific heats to track second order transitions. So at a second order transition, we will basically get a divergence in our specific heats, right. and the key thing is these divergences will actually grow with cell size. So if you use larger and larger supercells, these divergences will actually increase in magnitude, and that's a very telltale signature of a second order phase transition. And these divergences will increase with cell size because second order transitions typically happen in form of waves. So if you have a larger system, your system can basically accommodate larger waves, and larger waves indicate sharper spikes in your specific heat. Right. So for first order phase transition, it's easy to sort of distinguish them. Second order phase transitions, you need to look at specific heats. Okay, and in Monte Carlo, especially when you want to construct phase diagrams, you typically do these constructions within the grand canonical ensemble, right. The popular terminology that's used for grand canonical Monte Carlo is Kawasaki dynamics, where you exchange for species rather than adding or removing a species. Right. So let's say you do Monte Carlo in a canonical setting, right. So in a canonical setting, your composition is fixed, right. So if you replace one A atom with another B atom, you have to at a different region of your system, you need to replace B with A as well. So one swap of A with B requires that another B atom is swapped to an A atom there, right. So that your concentration is fixed. So you can do canonical Monte Carlo, but canonical Monte Carlo typically leads to very slow convergence, right. So if you are interested in tracking phase transitions or constructing phase diagrams, you can use canonical Monte Carlo, but the amount of Monte Carlo steps or sweeps that you will need to arrive at averaged quantities will be larger, and hence your phase diagram construction will be slower. But if you do the same exercise in grand canonical Monte Carlo, right. So here you just every perturbation is basically an exchange of species. So you exchange A with B or B with A, right. And you are basically equilibrating with your system against some kind of an external chemical potential, right. So you have a reservoir of A atoms or B atoms, and then you are equilibrating your system as a function of different chemical potentials. So researchers have shown that grand canonical Monte Carlo or Kawasaki dynamics converges to thermodynamic quantities faster, way faster compared to canonical Monte Carlo, right. So typically when you are interested in constructing phase diagrams, you typically do grand canonical Monte Carlo sweeps or grand canonical Monte Carlo steps, right. And you track first order transitions based on discontinuities in your chemical potential as a function of composition, and you track second order transitions based on your discontinuities in your or divergences in your specific heat as a function of temperature, right. So typically what you do is you do grand canonical Monte Carlo sweeps as a function of temperature and as a function of chemical potential. So if you were doing canonical, you do temperature and composition; grand canonical, you do temperature and chemical potential. What are some of the hyperparameters associated with Monte Carlo? So random seed, or how you generate the random numbers. So basically the way you choose atoms to perturb is based on some kind of a random number generator. So depending on the random number that you generate, you choose an atom and then introduce a perturbation at that atom or at that site, right. So what kind of random seed or random number generator is a hyperparameter? It's a small hyperparameter, but this is something that one needs to keep in mind. What kind of initial configuration we choose to begin our equilibration and sampling of our Monte Carlo, this can really bias what kind of transition temperatures or transition compositions or even diffusivities that you can actually get in your system. Supercell size is very important hyperparameter. Typically larger the supercell, the more converged your results are, but the more computationally heavy they are. Number of Monte Carlo steps or sweeps for equilibration, this is a very important quantity, and also how much do you sample, this is again an important quantity. Rule of thumb is you at least need about 1000 sweeps of sampling for robust statistics. So you at least need 1000, you may need more, right. And the range of temperature and chemical potential, this is also a system dependent quantity, and hence it's a hyperparameter, right. So you need to carefully choose how much you are going to sample in terms of temperature and also chemical potential. So I'll just show a few examples of cluster expansions on Monte Carlo. So this is an example from a fairly old work. So this is 2002, where the authors used very small data sets. So you see that number of data points that were used to construct these cluster expansions were very small, and then they subsequently used Monte Carlo simulations to basically construct phase diagrams. So this is phase diagram in a titanium aluminum system, this is silicon germanium, this is magnesium oxide and I think calcium oxide if I am not wrong, and this is copper gold. So these are all systems with practical relevance, and the authors managed to construct phase diagrams with fairly reasonable accuracy. You can also do there are also more modern examples of phase diagram construction in more complex systems as well. So this is an example of phase diagram in zirconium oxygen system, so or zirconia basically. So it's a basically phase diagram as a function of oxygen content here, and you see that the phase behavior is fairly complicated. This is all generated based on cluster expansions in Monte Carlo. This is basically one of my older works where we looked at how what is the phase behavior as magnesium sort of intercalates into a battery electrode. So the electrode composition is V2O5 here. So as magnesium intercalates, what kind of phase diagram you can actually expect from this system. So these are all phase diagram constructions. You can also do diffusivity calculations. For diffusivities, you may need to modify your cluster expansion framework. So you may need to construct what is referred to as a local cluster expansion, and then couple that with kinetic Monte Carlo. Once you do that, you can get very nice diffusivities as a function of concentration and at different temperatures here. Right. So this is an example of a recent work that I was a part of where we modeled how well sodium ion diffuses in a solid electrolyte material for sodium ion batteries. So in our hands-on session, so which will follow this lecture, we will build a fairly simple cluster expansion and also run some sample Monte Carlo. So please do take that exercise and try your hands at building a cluster expansion and running some Monte Carlo. There are lots of packages that you can use to build cluster expansions. So you can use what is referred to as SMOL, you can use CHASM, AT and also ICET. So you can use several, there's a whole zoo of packages available for building cluster expansions and also doing Monte Carlo simulations on top of them. With that, let's summarize and finish this lecture. So at the beginning we looked at lattice models and cluster expansions being a very important lattice model. We can use these techniques to generate fairly simple physically intuitive models. There are also hyperparameters associated with cluster expansions, and we also briefly looked at Monte Carlo. We looked at Metropolis algorithms in a more detailed fashion compared to kinetic Monte Carlo. So you can use Metropolis to get phase diagrams, kinetic Monte Carlo to get diffusivity maps and so on. So we basically see how we can combine different lattice models, sampling techniques along with statistical mechanics or statistical physics to get phase behavior and diffusivities as well. So very important thermodynamic and kinetic properties of a given material. So with that, we come to an end of the second module of this course where we looked at more physics driven calculation techniques as well as physics driven models. In the next lecture we will be moving towards more advanced machine learning models, and we will start off with machine learned interatomic potentials. With that, I thank you all for joining today. I will see you in the next lecture.